All right, chemistry, this is your video lecture for chapter 3, section 3. This section is called Counting Atoms. What I'm wanting you to be able to do here, I want you to be able to compare the mass quantities for units, and units for atomic mass, with those for molar mass. We'll be talking about those two items, atomic mass and molar mass. And yes, there is a difference. You will have to know that difference and describe it. Define mole. This is one of the central things to chemistry and is not going to go away for the rest of the year. So define mole and explain why this unit is used to count atoms. Calculate either mass with molar mass or number with Avogadro's number given an amount in moles. And here's where we go back to conversion factors. I will give you an amount in moles, and you are going to convert that to absolute mass or the number of particles, either using molar mass or Avogadro's number. You'll also need to discuss atoms of different elements in terms of their numbers of electrons, protons, and neutrons, and define the terms atomic number and atomic mass. And lastly, define isotope and determine the number of particles in the nucleus of an isotope. All right, so we got a lot of stuff to hit. Let's get going. Let's start with the atomic number. The atomic number is the number of protons of the nucleus. The atomic number is the same for all atoms of an element. So because each element has a unique number of protons in its atoms, no two elements have the same atomic number. There's no chance of you finding a carbon atom and an oxygen atom that have the same number of protons. It's simply not possible. So, another example, the atomic number of hydrogen is 1 because the nucleus of each hydrogen atom has 1 proton, whereas the atomic number for oxygen is 8. There are 8 protons in a nucleus of oxygen. Atomic numbers are always whole numbers because, obviously, you cannot have half of a proton or a third of a proton. You can only have a proton or not. So they always occur in whole numbers. The atomic number also reveals the number of electrons in an atom of the element. So what we're doing is, if we're assuming that the atom is electrically neutral, that means that the number of negatively charged electrons must equal the number of positively charged protons. Let's look at an example here. We have oxygen. We have the atomic number. We have the symbol for the element. We have the name of the element as well as the mass of the element and then electron configuration, which is something that we'll talk about later. Over here to the right, we have the current model, at least as far as we're concerned, in this point in the history of our class, of the atom. So we have a nucleus where we're going to find protons and neutrons. And then we're going to have a certain number of electrons circling or moving around that nucleus in the electron cloud. So the atomic number for oxygen will always tell you that that atom has 8 protons. And if it's electrically neutral, it also means that it has 8 electrons. Now, there will be times in this class where we work with atoms that are not electrically neutral. Okay, those are going to be called ions, and we'll deal with that when we get there. So again, electrically neutral, 8 protons, 8 neutrons, 8 electrons. I can gather all of that from this 8 on top of the oxygen. The mass number is the sum of the number of protons and neutrons in the nucleus of an atom. So I'm looking at protons and neutrons to make the mass number. You can calculate the number of neutrons in an atom by subtracting the atomic number, again, which is the number of protons, from the mass number, which is the number of protons and neutrons, right? Since the mass number is just those two numbers added together, you can simply subtract one of them to find the other. This is how it would look in equation form. Mass number minus atomic number equals the number of neutrons. But unlike the atomic number, the mass number can vary among atoms of the same element because you can have a varying number of neutrons in the nuclei of atoms of the same element. Those are simply called isotopes. So, example. A particular atom of neon has a mass number of 20. Because the atomic number for an atom of neon is 10, neon has 10 protons. All right? So we're going to take that 10 protons and we're going to subtract it from that mass number of 20. And that will allow us to conclude that for this particular atom of neon, there are 10 neutrons in the nucleus. Again, let's look at this example. Again, we still have a nucleus. We still have protons and neutrons in that nucleus. We still have an electron cloud around that nucleus. But when we look at the periodic table, we see a 10 above the symbol for neon. The atomic number is 10. There are 10 protons in that nucleus. Now, when we look at the mass number below the name of the element, that's 20. That means that the mass number is 20. The difference between the mass number and the atomic number is the number of neutrons. Let's see. Let's look at a sample problem. How many protons, electrons, and neutrons are present in an atom of copper whose atomic number is 29 and whose mass number is 64? So, in order to throw this out, we're going to look at the atomic number, which is 29. That indicates the number of protons, so 29 protons. Now, copper, we're assuming that it's electrically neutral. So that means that the number of electrons must equal the number of protons. So the number of electrons is 29. So notice that we've already established how many protons there are and how many electrons there are. The last thing we want to do is determine the number of neutrons. So the mass number, which we were told by the question is 64, indicates the total number of protons and neutrons. But we do know how many protons there are, right? We know we're working with copper, so we know the atomic number is 29. So we're going to take that mass number, 64, and subtract the atomic number, 29. The difference between those two values will be the number of neutrons. In this case, it's 35. Each element has a name, and the same name is given to all atoms of an element. For example, sulfur, the element, is composed of only sulfur atoms. Each element has a symbol, and the same symbol is used to represent every one of that element's atoms. Atomic number and mass number are sometimes written with the element's symbol. So let's take a look at how that might look. The atomic number will always appear on the lower left-hand side of the symbol. Okay, so if we're going to use the atomic symbols, we have hydrogen, helium, lithium, beryllium, and boron, the first 5 elements on the table. We're going to identify how many protons they have, the atomic number, by writing that subscript lower left-hand side of the symbol. The mass numbers we're going to write on the upper left-hand side of the symbol. So here we can write a few examples. We have hydrogen, but hydrogen, even though we know by definition it's going to have 1 proton, it may or may not have neutrons. So notice we have hydrogen with a mass number 1 and hydrogen with a mass number 2. Hydrogen with a mass number 1, that indicates that there's 1 proton, no neutrons. Hydrogen with a mass number 2 indicates there's 1 proton and 1 neutron in order to get the mass number up to 2. Helium, by definition, the atomic number is 2. So in order to have a mass number of 3, we must have 1 neutron. With helium-4 over here, again, helium is defined as having 2 protons in its nucleus. In order to get to a mass number of 4, it must have 2 neutrons. And this system is going to hold true for these isotopes of lithium, for beryllium, and these isotopes of boron. Now, both numbers can be written with the symbol. Okay? This is not uncommon. You're seeing the mass number on top and the atomic number on bottom. So realize an element can be represented by multiple versions of itself. Here we have 3 examples of hydrogen. 3 examples of hydrogen. They're all hydrogen, but the mass numbers are going to be different. all atoms of an element have the same atomic number and the same number of protons, because that's what the atomic number is. But atoms do not necessarily have the same number of neutrons. They can, but they don't have to. So atoms of the same element, meaning they have the same number of protons, same atomic number, but have different numbers of neutrons, are called isotopes. One standard method of identifying isotopes is to write the mass number with a hyphen after the name of the element. So we have helium-3 or helium-4, or indicating the mass number of that specific isotope of helium. The second method of identifying isotopes shows the composition of a nucleus as the isotope's nuclear symbol. So whereas before we simply used the name and then the hyphen, here we're going to use the symbol. So you look at helium, and again, it's still helium-3 and helium-4, just like in the previous slide. But instead of writing out the name helium, we're simply using the symbol. All isotopes of an element have the same atomic number. Again, however, their atomic masses are not always the same because the number of neutrons of the atomic nucleus of each isotope varies. Let's look at two stable helium isotopes, helium-3 and helium-4. We can see in this graphic the difference between the nuclei. In helium-3, we have 2 protons because obviously it's helium. And in order to get to mass number 3, we have 1 neutron. To the right, we have helium-4. It's still helium, so we have to have 2 protons. But in order to get to a mass number of 4, we have 2 neutrons. Here are some examples, stable isotopes of lead. So we have lead-204, lead-206, lead-207, and lead-208. Notice how it's always 82 protons. It always has an atomic number of 82 because that's lead by definition. So what's changing here is the number of neutrons. In lead-204, we actually have 122 neutrons. In lead-206, we have 124 neutrons. In lead-207, we have 125 neutrons. And in lead-208, we have 126 neutrons. Now over here, we have percent abundance. This tells you how common that particular isotope is. Here, the largest percent abundance is lead-208. It's over half. So over half of the lead that exists on this planet is the type of lead, the isotope of lead that has 208 for a mass number. It has 126 neutrons. 22.1% of all lead is lead-207. 24.1% of all lead is lead-206. And 1.4%, the smallest percent abundance, is lead-204. Here's another example. We have carbon, carbon-12, carbon-14. Notice each carbon has 6 protons, but the mass number can change. We have a mass number of 12, which if you guys can do this off your head, that means it has 6 neutrons. This carbon over here, by definition, has 6 protons, but how many neutrons does it have? 8. Right? The difference between 6 and 14 is 8, so 8 neutrons. Here's another sample problem. Calculate the numbers of protons, electrons, and neutrons in oxygen-17 and in oxygen-18. So we can take the atomic number, and we can say that that is the number of protons, because that's what the atomic number is. So for oxygen, that's going to be 8. So if we have electrically neutral oxygen, the number of electrons is going to be 8 as well. So that's pretty quick, pretty fast to get 2 of those 3. In order to find the number of neutrons, we're going to take the mass number and subtract the atomic number from it. So when we're talking about oxygen-17, we're going to subtract 8 from 17, and we'll get 9. That's 9 neutrons. For oxygen-18, we'll take 18 and subtract 8 from it, and that will give us 10 neutrons. So for oxygen-17, there are 8 protons, 8 electrons, and 9 neutrons. For oxygen-18, there are 8 protons, 8 electrons, but 10 neutrons. All right, new topic. Atomic mass. You would not expect something as small as an atom to have much mass. For example, copper atoms have an average mass of only 1.0552 times 10 to the negative 25th kilograms. That's incredibly small. Each penny made of copper has an average mass of 3.13 times 10 to the negative third kilograms and contains copper only. Here's the question. How many copper atoms are in one penny? This is the type of question you're going to want to be able to calculate. Assuming that a penny is made up of pure copper, okay, just copper, and earlier in the year we established that the penny is not pure copper, but if we assume it is, so that all of this mass, the 3.13 times 10 to the negative third kilograms, is all copper, how are you going to calculate how many copper atoms are in that mass? Well, we know that one atom of copper has a mass of 1.0552 times 10 to the 25th kilograms. And no, you don't have to know that off the top of your head. We know that because the question told us up here. So we know that one atom of copper is equal to this mass. Well, we can use that, guess what, as a statement of equality to create a conversion factor. So we have a mass, one penny, of 3.13 times 10 to the negative third kilograms, and we'll set up a conversion factor with atoms of copper on top and kilograms on bottom. This way, kilograms will cancel out, and atoms of copper will be the only unit we have left. So when I calculate this value, I'll have some number of atoms. Now, what I want to point out to you is when we actually carry out this calculation, we're going to have a times 10 to the negative third divided by a times 10 to the negative 25th. So when we're looking at this exponent, for what this exponent is going to need to be, it's going to be negative 3 minus negative 25. Negative 3 minus negative 25, which is going to end up being positive 22. That's why we went over the functions using scientific notation and how to calculate those numbers. So the M value is just 2.97. You just get that from your calculator, but it's times 10 to the 22nd copper atoms. That's a lot of copper atoms, guys. We have to move this decimal to the right 22 times. That means there are 20 zeros after that 297. 20 zeros. That's how many atoms are present in one penny. That's a lot, guys. A special mass unit is used to express atomic mass, right? The mass of one single atom. This unit has two names. Okay, one of them is the atomic mass unit. We call them AMUs. Or you could also use the Dalton, capital D, lowercase a. Mass number and atomic mass units would be the same because a proton and a neutron each have a mass of about 1 AMU. If you remember from last section, in one of the tables in our notes, we saw that the mass of the proton and the neutron are not exactly the same. However, they're incredibly close to being the same. So for the rest of this course, we actually are going to pretend like they're the same mass, because the difference is so negligible that it won't make a difference for our purposes. Okay, if you're doing high level, physics or chemistry calculations, that can make a little difference in what you're doing, but for our purposes, we're going to pretend that they have the same mass. Now, the AMU is really handy because an AMU is essentially defined as the mass of a proton or a neutron. So if you have one proton, you have one AMU. If you have two protons, you have two AMU. If you have three neutrons, you have three AMU. It's set up to be fairly straightforward and simple like that. So for an example, a copper 63 atom has an atomic mass of 62.940 AMU. 63, and that number is incredibly close to 63. That's why. It makes it very handy for us. As opposed to a copper 65 atom, which has an atomic mass of essentially 65. On the periodic table, the mass is shown as an average of the atomic masses of the naturally occurring isotopes. So if we go and look at the examples we used on the last slide, copper is listed at 63.546 instead of the 62.940 or the 64.928. It's an average of those two isotopes. You guys following what I'm laying down? We have copper 63, which is the 62.940, and we have copper 65, which is the 64.928. We're going to take the average of those masses, and we'll get what we find on the periodic table under copper, which is 63.546. All right, so my favorite thing in the world, the mole. Most samples of an element have huge numbers of atoms, huge numbers. Refer back to the calculation we did with the copper atoms, and you can see how many atoms there really are. The mole is defined as the number of atoms in exactly, right, not just significant figures, but exactly 12 grams of carbon-12. 12 grams of carbon-12. The mole is the SI unit for the amount of a substance. How much of the substance do you have? We're going to report that in moles. The molar mass of an element is the mass in grams of 1 mole of an element. So if you have a mole of an element, if you take the mass of that mole, that'll be the molar mass, the mass per mole. Molar mass has a unit of grams per mole, or G over mole, M-O-L. Now, the mass in grams of 1 mole of an element is numerically equal to the element's atomic mass from the periodic table in atomic mass unit. So, what does that mean by looking at it? If we look at iron, okay, if we have a mole of iron atoms, which is 6.02 times 10 to the 23rd iron atoms, that's what a mole is defined as. That's 1 mole. Notice how the numbers are the same for 55.78 grams of iron and 55.78 grams per mole of iron. Notice how those numbers are the same. Scientists have also determined the number of particles present in 1 mole of a substance. This is called Avogadro's number. This is really handy for us, and you guys will see that in the future. That 1 mole of a pure substance contains 6.0221367 times 10 to the 23rd particles. That is known as Avogadro's number. And Avogadro's number may be used to count any kind of particle. So that's going to include atoms or molecules. So how do we use that? If we're given a certain number of moles, I can use the grams per mole, its molar mass, to convert from the number of moles into the mass that I have. If I'm given a mass, I can use the, again, molar mass to convert from the mass to the number of moles. The only thing I have to adjust is which term is on the numerator and which term is on the denominator. So let's look at a sample problem. Determine the mass in grams of 3.5 moles of copper. So first make the setup that shows what is given and what is desired. I've been given 3.5 moles of copper, and I want grams of copper. Now I'll use a conversion factor that has grams of copper in the numerator and moles of copper in the denominator, so that the appropriate units will cancel, and I'll be left with the appropriate units. So I'll set something up like this. So I have the 3.5 moles of copper, and then I have my conversion factor with grams of copper over 1 mole. Now, what number do I throw in for that question mark? I'll look at the periodic table. And the periodic table will tell me that the conversion factor is the molar mass of copper, which is 63.55 grams per mole. So I will throw the 63.55 into this question mark here. So in my calculator, I'm going to go 3.50 times 63.55 divided by 1. Notice the mole unit is going to cancel, and the only thing I'm left with is grams of copper. And that's what I want because the question is asking me for the mass of copper in grams. The calculator and the appropriate number of significant figures tell me that that is 222 grams of copper. Let's try another sample problem. Determine the number of atoms in 0.30 moles of fluorine atoms. So to determine the number of atoms, select the conversion factor that will take you from the amount in moles to the number of atoms. Now, in order to do that, I'm going to take the amount, or the moles, and I'm going to set up a conversion factor using Avogadro's number. And it's going to look something like this. I have the amount of moles that I've been given, right, the 3.50 moles of fluorine. In my conversion factor, I'm going to have moles of fluorine on the denominator so that that can cancel. And then I'm trying to determine the number of atoms. And if I'm trying to determine the number of atoms, I'm going to use Avogadro's number on that numerator. Notice that the moles of fluorine will cancel. And so fluorine atoms is the only unit left over. And after carrying out that particular function, the 3.50 times 6.022 times 10 to the 23rd, I reach an answer of 1.8 times 10 to the 23rd fluorine atoms. I think that should be times 10 to the 24th. Yeah, I'm pretty sure that should be times 10 to the 24th fluorine atoms. Typo. So originally, atomic masses expressed the atomic masses expressed the ratio of the mass of an atom to the mass of a hydrogen atom. So we were comparing everything to hydrogen. Using hydrogen as the standard turned out to be pretty inconvenient because hydrogen doesn't actually react with very many elements. Because oxygen combines with almost all other elements, oxygen later became the standard for comparison. This choice also led to difficulties because oxygen has 3 isotopes. So what do we do here? How can we agree on a standard? In 1962, a conference of chemists and physicists agreed on a scale based on a single isotope of carbon. This is used by all scientists today. This scale defines the atomic mass unit as exactly 1/12 the mass of one carbon-12 atom. Again, that's carbon with a mass number of 12. As a result, one mass unit, okay, the atomic mass unit, the AMU, is defined as exactly equal to 1.6005402 times 10 to the negative 22nd kilograms, which is a very small mass. But remember, 1 AMU is roughly equal to 1 proton and 1 neutron. All right, that's going to do it for this set of notes. I know this is a long lecture, but we have a lot of content to cover in this section. I will see you next period.